All right, everybody. We have a request to do a roadmap from the COVID semester where we couldn't have boxes to fill in. So let's just do it as if these are boxes. Every letter is really a box on your test. It's good questions. If I had to name this, I'd say it's called an allylic chlorination. That's where we use radical. So A, you need to have a generator of radicals called chlorine and heat to get the thing initiated. And then you generate an allylic chloride. HCl is the side product, if you're curious. You also generate HCl. It's not a very nice looking Cl. Getting worse. Plus HCl. All right, what's happening in B is some kind of substitution. How about using a nice nucleophile? KSH comes to mind. I don't need a solvent here unless it says I do. You could put a nice SN2 solvent if you want, but it actually would work with an SN1 solvent too. Primary allylic is about as stable as secondary, 2.5 for a leaving group. And that gets us an SH on there. And C, the answer is almost right there. It says you're going to generate HOET and take the H off of sulfur. So I think you're going to use a base with OET minus. And if you're not worrying about cations, you just do this and say, I don't care what the cation was. There you go. And that would generate HOET because O minus took the H off S. I know you're not responsible for the pKa of a thiol, but you are responsible for knowing it's less than the pKa of an alcohol. Because in chapter 4, you learned trends on the periodic table. And as you go down a column, O goes down to S on the periodic table in group 6, pKa goes down. So yes, this base is plenty strong to take the H off of that. And when we come back after the test, we'll learn the pKa of a thiol is actually closer to 10. Okay. Definitely looks like I'm setting up for an SN2. Do you know why? Well, I've got an SN2 solvent here. That's a big giveaway. I want you to do an SN2 between these two molecules. 2, 4, 5. With a BR here on a wedge to make it R. And that's going to give product U right here. And backside attack on an R gives an S. And you're supposed to draw it, so I guess I should draw it. And it's going to be a, what's my solvent? My nucleophile is a sulfur. Dash to a sulfur with an allele on it. And that pushed the old hydrogen out here. There's product U with the worst drawn dash I've ever seen. Semi better. Okay. That's U. I like to set these up. If I have a sulfur in my molecule, you probably, well, some of you may be noticing he likes to react an alkene to set up an NGP later. Oh, look at that. He's not even hiding it here. Yeah, should stop talking to about myself in the third person. I know it's not healthy. All right, so HBr is going to react with our alkene to generate a secondary alkyl bromide as the major product. That is chapter 6 all over again. We're going to go to V. And we're going to generate, I don't know. I'm getting tired of drawing this R group. You're allowed to do this on tests too. Everything there up to, but not including the S, is now called R. So R has a dash to an S. which goes CH2CC with a new BR right there. And that is product V. I'm going to go ahead and do the mechanism for the NGP. And that's the only time I really have to do a mechanism myself to figure out what's going on is the NGPs. Just can't see them directly myself. Others may be more gifted, but you know, that's okay. Do the best we can. R dash 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 to an S, up to a CH2, down to a C with a methyl. New bond here, triangle plus. The question for NGP is, which carbon attached to sulfur in the triangle is the easiest one to get to? That's just like saying which one is least hindered. And that's the CH2 here is less hindered than the C with a methyl down here. And that's where your HOET does its attack. So HOET does its attack here. And you're going to get popping open of the triangle. Sulfur with this red bond here to carbon with a methyl comes up to a CH2 with an OHET. And you never have those as final products. That's an oxonium. Solvent neutralizes it. And you've circled R, so you never have to draw it again. He's going to go all blue here. And it's not a mechanism question, so you don't have to show me how we lost the H, but if you want, here it is. Didn't have to show this. Here's how it happens. Solvent grabs H. Oxygen gets neutralized. There. Finally, product W. Do some yellow circles here, I guess. W, U. There you go. Now, what about alkene with bromine? No heat on this one. That's the chapter 6 one. So going down to here, step 1 gives dibromide. Step 2, KNH2 excess. On your test, I would have been nicer and said, there's a clue that you're gonna do eliminations right here. Isn't that a clue to you? I'm hoping. I'm just hoping that that's a clue to you. You need to do E, elimination. But I really should have had heat here. That's not a bulky base. That was an oversight on my part. I am confessing right now. So strong base heat, E2, you're going to do E2 times 2. I'm going to write that down, E2 times 2. You got 2 leaving groups. Each one makes a new pi bond. You've made product Z right here, almost. What? When does this end? That's not Z yet. You know why? You know why? Because this is what you get after E2 times 2, and I'm pointing out it's a terminal alkyne, which has a pKa of 25. And if I have excess NH2 minus floating around, which I do, you also get an acid base at the end here. So you're going to get partial credit if you draw this as the product. I'm going to give you something because you do know what's going on. But you forgot about your pKa's. And when you have excess of a strong base around, this would be mole number 3 that does this. Moles 1 and 2 did the E2s. Mole 3, that's a minus in there. I can't get it to look like a minus. Ah, I did. Mole number 3, acid base, gives product Z. That's Z. Strong nucleophile with a methyl on the end. Over here, I got the methyl on the end, C-triple-C. I need to add a benzyl bromide. What's that mean? Phenyl attached to one more C is benzyl, and bromide will get you to this drawn thing here. So that'll be box D, and I'll do it like this. Here's D, benzyl bromide, a leaving group on a carbon, one away from a phenyl. I don't need a solvent there. If you want to give me a solvent, that'd be great. They're only 1 point each though, so I didn't really need more than one thing. And what about Cl2 and heat? You want to make the best radical out of this thing possible. You have these positions here that are the best H's to take. This is benzylic secondary. If you look at your chart, I think 360 kcals per mole to get that, but it's not just benzylic, it's one away from a triple bond. So it's kind of allylic too, even though that's a triple instead of a double. And this one's just kind of allylic. There's no benzyl component. So of all these things, this is by far the easiest H to make a radical from. If you put a dot there, and then you attack a chlorine and you put a chlorine there. This is a long-winded way of saying you're going to do a benzylic chlorination. So Y is going to look like this. I'm going to try to write it right above Y because space is becoming a thing here. Phenyl goes to C-triple-C methyl with a Cl on here. And there's your Y. Your Y. And then that is a molecule that could generate a carbocation par excellence, as they say, with excellence. Secondary benzylic, and what it looks very much allylic too. That's like a 6-degree cation. Well, 5 degree, 2 plus 1.5 plus 1.5. Anyway, all I'm trying to say is carbocation here, O goes there. You get an oxonium right here with O attached to ethyl and H. Please don't finish with oxoniums. Neutralize the oxonium, put O ethyl there, and call that product X. Here I'm drawing product X. A lot of talk. We got phenyl.
Last one is a dehydration, right?
I'm sorry?
The last one is a dehydration.
We got heat only to speed this reaction up. No, there's nothing to dehydrate here.
Oh, okay.
There's no leaving group whatsoever.
Oh, I see.
Yeah, we did an SN1. It's misleading sometimes when you see the heat, you say, oh, I got to do an elimination to make a pie. But no, that's only if there's a strong base present. And there's no strong base. So the heat here is just to speed up what might otherwise be a very slow SN1. Remember, heat speeds up every reaction. When does heat cause elimination? When there's a strong base present, and we don't have a strong base present. There you have a roadmap from the past. I hope this was helpful.
Thank you.
All right. Any last minute questions?
I'm fine. Thank you very much.
You're good. All right. I'll be posting these within the next 20 minutes. And go blue.
Yeah.
I have one question that's not related to what we are doing.
Sure.
It's a BDE question. When would we have, can you refresh my memory when we would have 2 initiation steps? Like initiation.
That's only for that anti-Markovnikov. It's gotta be HBr. There's no other one that works.
Okay.
And it's gotta also have a peroxide present. So you need
Okay.
HBr with a peroxide and heat. That combination is the trigger for you to do anti-Markovnikov addition of HBr to your alkene.
Okay.
And that was found in the middle of chapter 8. It's the one that's not as important as that our original initiation, propagation, termination reaction that we learned.
Yeah. Okay. Thank you.
That's the one with 2 initiations. You're welcome. All right, ladies and gentlemen, good luck.
Thank you.
See you Monday.
Thank you.
Bye.
Thanks.